Hi, welcome to the virtual problem solving session on shafts and shaft design. We're going to look at two problems this week, and the first problem is more of an analysis problem where you're given the dimensions of a particular location at a shaft, you're given the material properties, and you are trying to figure out the factors of safety. So we'll just jump in. At a machined shaft shoulder, the small diameter is 1.125 inches, the large diameter is 1.75 inches, and the fillet radius is 0.12 inches. The bending moment is 1,300 pound-inches, and the steady torsion is 1,100. The heat-treated steel shaft has an ultimate strength of 110 KSI and a yield strength of 85 KSI. The reliability goal for the endurance limit is 99%. I will also add that we are assuming room temp and no additional effects that may worsen fatigue. So determine the fatigue factor of safety of the design using the modified Goodman failure criterion, and then also determine the yielding factor of safety. We want to determine the yielding factor of safety because if we determine that the yielding factor of safety is less than 1, it's an indication that the part's going to fail on that first cycle of loading, and hence fatigue isn't even an issue. Okay, first step, draw a picture of the machined shaft shoulder, including dimensions. So again, we're just drawing a portion of the shaft. We're just drawing and analyzing one location. So the dimensions won't be to scale, I'm sure, but here we go. We have torsion, and then we have bending moment, and it is fully reversed, so it's going, oh, I have a straw right here. So you can picture it, you know, shaft is kind of doing this as it's rotating. So D equals 1.75 inches, big D that is. Little d is 1.125 inches. Fillet radius is 0.12 inches. Okay. So first step, find the corrected endurance limit. So that would be SE, and to get to SE, we have to do the whole Marin equation thing, and we start with SE primed, which is the the lab value for endurance strength without all of the fatigue factors applied. And this is a simple calculation, 1/2 SUT. So this is in my analysis tool, which I'll show you here shortly. And then all of these factors are in my analysis tool as well. So some of the questions came up today in Zoom hours about how you should set up your tool, and the answer is simply. So I will share mine with you now. All right. So I have this same setup for metric units, but I'm just going to show you English units just to make it not so cluttered. So you'll see I've entered 110 KSI for the ultimate strength, 85 for the yield. SE primed is calculated automatically. Ka depends on the surface finish, and that coefficients A and B, or factors rather, A and B, factor A and exponent B, are from table 6.2. You can spend the time to program these in and have an if surface finish is ground, then A is this, B is this. It's going to depend on your unit system. I just look at the chart and put the numbers in. KB, I do have a simple if-else statement. So KB is the size factor, and if you remember, there are 4 different versions of KB, 2 for English, 2 for metric, and it had to do with the size of the diameter. So for KB less than or equal to 2, you see up at my equation bar here, I have one form of KB, else the other form, because there are only 2 options. So that's a really easy if-else statement to do there. And that is reading the diameter directly from cell H27, which, as a reminder, is the smaller diameter, because that's really our critical point of interest, is where that small diameter is intersecting with the larger diameter, but we use the small diameter. KC1, so we have combined loading, but we're going to deal with the combined loading through the von Mises stress equations. KD, room temperature, so that's 1. KE, reliability factor. So again, it's just a chart, just easy to pop down here and read it. 99% corresponds to KE of 0.814, so I type that in. KF is 1. We don't have any other information about damaging effects. So that's all I need to calculate SE primed. So you'll see that it's referencing SE rather. So you'll see that SE is referencing SE primed and all these Marin factors. Note that since I've entered in SE prime, SUT, and therefore SE primed in KSI, the SE is going to come out in KSI. And you just have to be mindful of your units, but I'll talk about when that's going to, might cause you some troubles later. Next, calculate the fatigue stress concentration factors. So we need KF for bending and KFS for shear. And to get to these steps, you'll need to reference tables for KT, KTS, Q, and QS. So we have a round bar in bending and in torsion. So these two figures from Appendix A, I think it's A15, are most appropriate. The things to enter, so we need to take into account our fillet radius of 0.12, little d 1.125. I have it in my Excel tool as orange because it tells me that I'm referencing it from somewhere else. So this D is coming from this D here. 1.75 is our big D. I haven't entered that anywhere in the tool, so it's a yellow input. And then R over little d and big D over little d are automatic outputs. So if we kind of line this up, R over little d on the horizontal axis. I really like just using lines in Excel. It makes it, easy to read. So to do that, insert, shapes, line, draw a line, and then, you can give it a color. You can change it, the weight, etc. So just makes reading these graphs a little less painful. Big D over little d about 1.6. So I've kind of tried to position it. So hard to see. So it looks like about 1.41. So that would be our input for KTS, which I have. And then for torsion, same R over D ratio, and then, same big D over little d ratio. So that looks like it's matching up to about this is 6, so 1.68 maybe. So just get as close as you can. Q, we have to read Q. So our fillet radius is 0.12, and when you're using these tables for Q, notch is just the general term for any hole or fillet radius for the the round part at the start of a keyway. So notch is just that general term. So 0.12, 0.12, English units are on the bottom, metric units are on the top. And we have the ultimate strength is 110, so it looks like Q is about 0.87, and then QS is about 0.91. So that's where I have these. And then KF and KFS should be calculated automatically from that. So report our values. Notice how KF and KFS are going to be lower than KT and KTS. And we talked about that with fatigue, with cyclic loading, you get a little bit of, the material gets kind of a little stress relief because of the fluctuating loads. Okay, so visually characterize the applied loads, include both shape and magnitude. So we have bending moment in pound force inches. It's fully reversed. And it's fluctuating between 1300 and negative 1300. Torsion is steady. And 1100 was our value. So that's all you have to do. On the midterm, I'll probably ask you to make a similar sketch. It just helps me understand if you understand what the stresses look like and helps me kind of follow your problem solving process. Okay, so find values for the alternating and mid-range components of stress caused by the loads characterized above. So if we look at these, this is a bending moment, so it's going to cause some bending stress by our old friend, the flexure formula, and then another old friend, the shear stress formula. I haven't taught mechanics and materials in years, but yeah, I remember the equations. So what we do with this step is remember that we have to include our stress concentration factors, and we're also going to be able to use a more simple expression. We don't have to find the moment of inertia because we have a solid round shaft. So I'll show you what this looks like. So don't forget your KF. It's a super common mistake. And we can do a little simplification here. This becomes, okay, and this just is from the fact that moment of inertia is pi d to the fourth over 64. And then C is d over 2. So that's how that simplifies. Okay, and then for mid-range shear stress, KFS, for J. All right, so that's a lot of scribbling. What goes in your analysis tool? This goes in your analysis tool, and this goes in your analysis tool. Let me show you. I have my loads entered over here. I found it easiest, you can take my word for this, to input moments and torques in pound inches if we have English units, because that's going to work out nicely to PSI, and your diameter is going to come out in inches when we are using an equation 7, 8, which we're not using for this problem, but you're just going to have less error. And so you get sigma A and tau M. So those are values that are calculated from the moments and the diameter, no problem. Hypothetically, we could have a sigma M and a tau A. So in other words, a mid-range value of bending moment and an alternating value of torque, but our loading case is not that. So here, I mean, we do have a mid-range bending moment, sigma M equals 0. And then we don't have any alternating torque. So it's not that we're just forgetting about those values, it's that they are truly 0. Okay, so reporting values, you get sigma M, if you're doing this problem along with me, 0, we just said that, tau A, 0, 14,802 PSI, and 5,403 PSI. Okay, cool. Moving on. Now we're getting into the von Mises stuff. So this was the preliminary to get us to von Mises, which eventually gets us to the factors of safety. So find values for the fluctuating von Mises stress. This is chapter 6, fatigue stuff, as a review. So our sigma prime A, when you see the prime, it's just telling you that we're talking about von Mises stress. So everything that's alternating goes up here. Everything that is mid-range goes down here in this equation. 3 tau M squared 1/2. Okay, so what goes to 0? This goes to 0, and this goes to 0. So sigma prime A is really just sigma A. Sigma prime M is not just tau M because of this 3 here. So back to my analysis tool. Okay, so you can see those entered. Sigma prime A, sigma prime M. Sigma prime max, so the maximum von Mises stress is just the sum of sigma prime A and sigma prime M, so add that one in because you'll need it when we calculate the yield factor of safety. This is 9358 PSI. Remember to keep including your units the whole way through. Okay. Report the factors of safety for both fatigue and yielding. For fatigue, 1 over the fatigue factor of safety. This is the modified Goodman approach, remember. So in my analysis tool, all right, so some things I see a lot. So one of the errors I see is forgetting that that formula was 1 over n equals blah, 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 blah. So make sure you are accounting for that. So your factor of safety, let's just go back. So this is how you should enter it. I don't really want to write that all out. Okay, 1 over that. So here's some potential pitfalls. Remember that we have our sigma prime A, and sigma prime M in PSI because that followed nicely from the way that we entered in the moment and the torque. But we entered in the ultimate strength as KSI because to read the Q and to figure out spacing out, we had to have SUT in KSI. So you can change it earlier. I just change it down here, or make sure that all the units are matching rather. So NF, so you'll see that I do sigma prime A is entered in as PSI, but then I'm dividing that by SE times 1,000, and then same thing, sigma prime M divided by SUT times 1,000. So just make sure your units match up. Seems simple, but I can't tell you how many times I have diagnosed that error in these tools. All right, so we get 1.74 for our fatigue factor of safety, and then our yielding factor of safety is just the ultimate strength, or the yield strength, sorry, divided by the sigma prime max. So I'll write that for you. So yielding NY equals yield strength over sigma prime max. Okay, and then reporting values got 1.74 and 3.52. So first cycle yielding is not an issue, and it looks like fatigue isn't an issue. So this component would have infinite life, at least as diagnosed from this one point on the shaft. Okay, so pretty simple. The next example we'll do will be where you don't have the diameter, and it's a way more realistic design problem. But I think learning the analysis is a really good first step. So you have to know how all these K factors interact, and we had to kind of remember what von Mises stress was and how to find the factors of safety. So stay tuned for a more difficult problem.